execution context and return, again, almost right away. So thread 1 has now queued up this action to run. And then thread 1 hits console.readline, which again, I've placed here to ensure that our program continues executing in the background and doesn't end as soon as thread 1 is done. Now, in the background, this DomeTrain task.run is going to run on a background thread. And because we've called continue with, we know that this code is going to execute using the same execution context, meaning it's going to run on the same thread. So that background thread now is going to call DomeTrain task.run. And then the background thread is going to write console.writeLine, the second DomeTrain task ID. So even though we've written it with starting thread, then first, then third, then second, what we should see is it prints out starting thread ID, first DomeTrain task ID, second DomeTrain task ID, and then third. So let's run this code and see how it looks. And there we go. Just like we expected, our starting thread ID was 1. Thread 1 queued up all of these DomeTrain tasks on the background, where it printed out the first DomeTrain task ID on thread 5, because thread 5 was just the first available background thread. And because we called continue with, we expected DomeTrain.run here to be queued up by thread 5, but executed on a different background thread, whatever thread was available. It looks like that thread ID was 9. So we're able to see here that continue with picks up that same execution context from the previous thread, essentially where it left off, in that we can even queue up new background threads from inside of our background threads by continuing to call DomeTrain.run. Now, for those of you following along running this at home, I do want to highlight that sometimes when you run this, there we go. Sometimes when you run this, you'll get the same thread ID for all of them. And that's kind of the nature of the beast when using the thread pool, because all this is saying is that by the time this DomeTrain task went to run, the first available thread in the thread pool was 4, because thread 4, in this case, had already printed second DomeTrain task ID of 4 and had finished and returned back to the thread pool. And then by the time .NET went to the thread pool to grab another free thread to run this DomeTrain task.run, thread 4 was available, it grabbed it, and it ran it again. So if you run this code multiple times, you might see that all 3 thread IDs are the same. It just depends on how quickly threads completed and what other threads were available in the thread pool for .NET to use. Now, this code doesn't look good. It looks weird saying that we're printing this line first, this line second, then we're jumping past and printing this line third, and then jumping back up to print this line fourth. It doesn't read well, and this code is prone to many, many bugs. So let's jump back to our DomeTrain task and implement .wait so that we can rewrite this code in a logical order that makes sense for us to read. Okay, back in our custom task, let's go ahead and create a new method. Public void wait. Wait is a blocking call. So we're going to use a .NET primitive called manual reset event slim to handle that blocking for us. Essentially, we won't dive deep into manual reset event, but basically what it is, it's a class in .NET that we can use to manage the thread's waiting behavior. So with .wait, it's a blocking event. So we can actually tell the thread to wait until a future event happens. And with manual reset event, what we do is there's a set method inside of it that will allow all the threads waiting on it to proceed. So let's write some of this code and hopefully it makes sense as we get a little deeper into it. First, again, we want to see if the task is completed. If it has completed, we can just move on. But if it hasn't completed, that's when we'll initialize our reset event and we'll actually call continue with, and the action we pass in is that reset event, and we call the set method. Now, what's cool with this is we're leveraging the continue with method that we've written, but this is actually exactly how .NET works under the hood. .wait also leverages continue with. Okay, so if it's not completed, then we need to wait for it to complete so that we can call the set event. And then we'll say reset event slim dot wait. And dot wait is what's going to block the current thread until it's allowed to resume. Now, this next chunk of code, this is going to execute once the task has already been completed. So if the task is completed and we found an exception, now what we could do is just throw that exception. And that kind of works, but the stack trace in that exception wouldn't include any of the code that led up to here. So we wouldn't have this .wait method and any user code that might have executed in between. We would lose it all. So to keep that stack trace, what we're going to do is leverage something called the exception dispatch info. And we'll tell that to throw this exception. That way we don't lose any information on our stack trace. The only thing I see missing here is we are touching completed. So let's make sure that we wrap this in a lock, because again, we're dealing with multi-threading and we don't want multiple threads to execute this code at the same time. One other thing we could do, let's move .wait down to here, and we'll just add a null check. It's essentially doing the same thing where we're waiting for this to complete if it's been initialized. And if is completed has not been completed, then this won't be initialized, meaning we won't wait. So it's essentially the same code, but we want to move this outside of the lock because, well, we don't want to lock on .wait because that'll cause a real bad deadlock. So it looks like .wait is now complete. So let's run back to our program and let's rewrite all of this nasty code to use .wait instead. Yes, we could use continue with, but the code will read much, much more nicely if we instead use .wait. So let's refactor this a little bit. We can get rid of some of these extra braces. And for DOM train task.run, we'll just say .wait. So now we know the next line of code won't execute until we've printed first DOM train task. And so now we know that this line of code won't execute till it's printed to the console. So this next line, we can be confident and say that the second DOM train task ID will be printed here. And then, yeah, let's do one more DOM train task.run. And again, get rid of some of the extra braces. And we'll say .wait again. And I can actually delete console.readline because what's going to happen now is thread 1 is going to start here. And thread 1 is going to print out starting thread ID 1. And then thread 1 is going to queue up this DOM train task on a background thread. But thread 1 is going to wait until this background thread that prints first DOM train task ID completes. Once that background task is done, thread 1 will continue and print to the console second DOM train task ID, which again, we're back on thread 1. So this should be second DOM train task ID 1. And thread 1 will again queue up another background thread to print out third DOM train task ID. And again, that's going to wait until that thread has completed before moving out of the next line. So remember, console.readline was just there because originally thread 1 was done. It kicked off a bunch of background threads. Thread 1 wasn't waiting for those background threads to complete before the program finished executing. So console.readline was there just to keep the program running while those threads were running in the background. But now we can remove console.readline and let's run this code and see what happens. Look at that. Okay, this is great. This is exactly what we wanted. Because again, we see that thread 1 was our starting thread, which is what we expect. But then we call DOM train task.run, which queues up a background thread. But in the meantime, it tells thread 1 to wait. So thread 1 hung out and waited for this background thread, which ended up being thread 4 to finish executing. And then thread 1 continued running. So we saw that second DOM train task ID is thread 1 again, because thread 1's picking up where it left off. And then again, we call DOM train task.run. But since we're calling .wait, thread 1's going to wait for this second background task to finish, which prints out third DOM train task ID, which ended up being 4, the same background thread that was used previously, was reused again. And the big difference here is now our code is actually readable. We can read line by line how this code is going to execute. And we don't need to worry about thread 1 finishing and terminating our program before this code moves on. So let's jump back into our custom DomeTrain task to implement task.delay.